Yeah, very good morning. Okay, so what we have done in the last class, I just want to go through it just once. And so Picard's theorem tells you about the existence and uniqueness of the solution to this so-called IVP, initial value problem. dy by dx equals to f of xy, and with initial condition y at x naught equals to y naught, and which can be equivalently represented in the following form. Okay, in the following integral equation. Then what Picard's iteration or Picard's approximation does is, so he has started with the zeroth approximation. Here the zeroth approximation, he has decided to work with the constant function, so with phi naught x equals to y naught. Okay, so for to starting purpose, so I already have mentioned, instead of this constant function you can choose any other function as well which will satisfy the initial condition. Okay, and then you can start with the looking for the next approximation and so on. Okay, so now, so once you have decided what is the zeroth approximation, phi naught x equals to y naught, okay, then you are looking for the new solution of the problem dy by dx equals to f of x y at x naught equals to y naught. So you want to construct the new solution by using phi naught. So that's, let's say that is a phi 1. So where the right hand side is replaced in terms of non things. So earlier the problem was here in the right hand side. If you look at, so this is the function involving unknown function. So this is why this integral cannot be solved. Okay, and we cannot get the analytical solution here. Okay, so for approximating point of view, we have to replace this integrand, okay, by some non-things. Okay, so what we have done is zeroth approximation is given by this constant function. Then first approximation is, so which we have denoted by a curve by phi1 of x, and this curve is drawn in such a fashion that this pairs x comma phi1 of x should be lies inside the rectangle only. Okay, so we are looking in the region, okay, R or rectangle R, so that can be decided later how large it will be. Okay, so so far it is mod x minus x naught less than equals to a and mod y minus y naught less than equals to b. Okay, so this a and b values can be decided later as well. Okay, and this v1 should satisfy this differential equation. Okay, and which has the equivalent form in integral form. You can say integral equation is this and these two are equivalent. So phi1 of x can be obtained by this integral equation. Now the integrand is purely a function of x only, which you can integrate easily, and you can get the first approximation. Okay, so this is known as Picard's first approximation. Okay, so previous was Picard's zeroth approximation. Now likewise you will construct now further approximation. So second approximation is, so by using this phi1 now you will construct a improvement, you can say. So phi2 be such that x comma phi2 of x belongs to R, and then phi2 will satisfy the differential equation that d phi2 by dx equals to f of x comma phi1 with the initial data phi2 of x naught should be equals to y naught, and then you can write in the form of equivalent form. Okay, so second approximation is essentially this phi2, which is satisfying this x comma phi2 of x in R, and it satisfies this following initial value problem. Then this is equivalent to say that phi2 of x is equals to this interval. So likewise you can proceed, and then you have this Picard's nth approximation is given by, so Picard's nth approximation So this is n plus 1th actually. Okay, so this is n plus 1th approximation will be Pn of Pn plus 1 of x equals to this. So you can follow the procedure here. Okay, now see, we wish to avoid theory here. So, but what is the conclusion is, if you if the Picard impose the same conditions that f satisfies that f is continuous and it is satisfying Ellipsis condition, okay, then this sequence of approximation will tends to the original equation. Okay, and that will give the guarantee. Okay, let's so we will are not interested in here. What we are interested in approaching the problem now. Okay, so now I just want to draw one example or two examples where we will see that essentially this Picard's approximation are tending to the analytical solution to the given equation. Okay, let's take one example. So the first example, very simple, we can take y dash equals to y, with y at 0 is equals to 1. And for which I hope the analytical solution, we are very much familiar that y is equals to e to the power x. Will satisfy this equation that that can be verified. Okay, right. Now we want to get now Picard's approximation. So from here, what is f of x comma y? So you have to fill that gap. Okay, comparison between this y dash equals to f of xy and y at x naught equals to y naught. So on comparison, what we found is f of xy is y, and x naught is 0, and x1 y naught is 1. Okay, now the very first thing is the function f satisfies. So so this is a polynomial, right? F of xy is equals to y, so it's y to the power 1. This is certainly clearly f is continuous and satisfying Ellipsis condition. That's very straightforward condition with, I can mention here, with L equals to 1. That is very simple to see. Mod of f of x comma y1 minus f of x comma y2 is y1 minus y2. Okay, so with L equals to 1, it satisfies the Ellipsis condition. On, we have to give a rectangle. So on any rectangle, any R, or you can say any rectangle R passing through rectangle R, what you can do is, I think, whose any rectangle R having 0, 1 as an interior point. Okay, we are as an interior point, not the boundary point. Okay, interior point. So you take any rectangle R covering this point. So F will satisfies both the conditions. So Picard's theorem is applicable, and hence it has unique solution, and solution will exist. So Picard's theorem implies that this equation, you can say, 1 has unique solution. Okay, so that which rectangle that you will decide, that you can decide later. Okay, so that you can is like you can get that edge and all by looking at the rectangle R. So mod y is less than equals to, or mod y minus 1 is less than equals to b. So you work out those things. Okay, so you can certainly find out that h. Okay, on you can say on I can write it mod of x minus x naught. So x naught is 0. Mod x less than equals to h. Okay, and where h is equals to minimum of a comma b by m. So you should fill out these gaps now. What is m here? Maximum. So it's a polynomial which will, if the boundary is going to be the if you just okay, let me complete it. So any rectangle R, so I can consider this x comma y such that mod of x minus x naught is less than equals to a. Mod of y minus y naught, that is mod of y minus 1, is less than equals to b. So now on this rectangle, you can see mod y is less than equals to 1 plus b. So okay, so this implies mod of f of x comma y is less than equals to 1 plus b. Okay, right. So it can certainly shows that this mod y is equals to, it can take the equality sign for 1 plus b. So this implies I can certainly say m equals to 1 plus b. From here, what will be the bound? M is maximum of f of x y, that's going to be 1 plus b. Okay, and so this will tell you what is h is minimum of a comma b divided by 1 plus b. Okay, so b divided by 1 plus b is definitely less than 1. So that now you can work with whether a is less than 1 or b a is greater than 1 and all those stuff. Okay, now what we are interested in the Picard's iterations. Okay, so now I'm just, so that is Picard's 0th approximation. Picard's 0th approximation. So let's keep it that v naught of x is equals to y naught, and that is y naught is given to be 1. Okay, for all x. Okay, right. Now, first approximation. So first approximation is v1 of x is equals to y naught plus integration x naught to x f of x comma v naught dx. So I am using this here abuse notation like y. Okay, y is treated as a function of x, so v naught is a function of x. So this is y naught is 1 plus integration x naught is 0 to x, and what is f of x comma p naught is v naught. So what is v naught? If you compare what is f of x comma y, is the, if you take the, if you give the input this pair x comma y, output the second this here second variable is y. Okay, so f of x comma p naught is v naught, and v naught of x is you have y naught, that is 1, so that's going to be 1 plus, I'm just writing x. Okay, right. Now what will be the second approximation? Second approximation is p2 of x is equals to, so you have to fill those, all those gaps, okay, in the notes. So y naught plus integration x naught to x f of x comma p1 dx. So that's equals to 1 plus integration 0 to x, and f of x comma p1 will give you v1 of x dx. Now p1 of x is 1 plus x, so this will be 1 plus integration 0 to x 1 plus x dx, and integrated what you will get is 1 plus x square by 2. And we can write something this later. So let's take one more approximation, third approximation. So third approximation is p3 is equals to y naught plus integration x naught to x f of x comma p2 dx. So for this particular problem, this f of x comma p2 is p2. Okay, so it's not for general problem. Okay, so y naught is 1 plus integration x naught is 0 to x, p2 of x is 1 plus x square by 2 dx. So that will give you 1 plus x square by 2 plus x cube by 3 into 2. So that is 3 factorial. I can write 2 factorial, and that I can write 1 factorial. Okay, so you can, so this previously it is 2 factorial. Here I can write to replace 2 by 2 factorial, and that is 1 factorial. So and so on. So you can also, if you are not convinced so far, okay, so you can also call, you can also calculate the fourth approximation p4 of x, and that you can show that 1 plus x square by 2 factorial plus x cube by 3 factorial plus x power 4 by 4 factorial. Okay, so where does this converge? This converges to, so nth approximation. From here I can write what is the final nth approximation will be 1 plus x square by 2 factorial plus and so on plus x to the power n by n factorial. So as n tends to infinity, this is the nth partial sum of the Taylor series of e to the power x, and this tends to the solution, this which is nothing but the analytical solution of the original equation, right? So this is the nth partial sum, or you can say n plus 1th, because n plus 1 term is there, so you can say nth or n plus 1th term. Okay, n plus 1th partial sum, okay, of this Taylor series of e power x. So this certainly converges to this. So we have the convergence of this Picard's approximation, at least for this problem. Okay, right. So let's take one more example. Okay, next example is let's say y dash equals to x plus y with y at 0 is equals to 1. Okay, now maybe later on you will able to see how the analytical solution will be this. So I am not right now finding or showing you how to identify that or how to derive this analytical solution. Okay, so I'm just giving you, this is the analytical solution for the given problem. So you can, so how do you verify? You can just substitute and at the present. So because so far you don't know any method so far, so or if you know, you can apply that. Okay, fine. So this is the analytical solution. We want to see whether the Picard's nth approximation or the sequence of approximation converges to this original solution or not. Okay, so if you compare, in this case, this f of x comma y is equals to x plus y, sum of these two. Okay, with x naught is 0 and y1 is y naught is 1. So on comparing, we got this. So I'm writing now straightforward, okay, all the approximation. So the 0th approximation phi naught of x is equals to y naught, that is 1. Okay, now using this p1 of x is equals to y naught plus integration x naught to x f of x comma p naught dx. So that's equals to 1 plus integration 0 to x naught is 0, f of x comma p naught. Now it is not p naught, please keep in mind. Now it is for this problem, so it is going to be x plus p naught. So x plus p naught dx. Now what is phi naught? For any x is 1. So what you will get is 1 plus integration 0 to x, and this is x plus 1 dx, and what you will obtain is 1 plus x square by 2. Okay, so far Yeah, you are saying you are able to see the pattern of previous example. Okay, right. First approximation, it matches. Okay, what about the second approximation? Is equals to y naught plus integration x naught to x f of x comma p1 dx. So that's equals to 1 plus integration 0 to x plus p1 dx. Now you substitute what is p1, integration 0 to x. What is x plus p1? Okay, so x plus p1. So p1 is this 1 plus x square by 2. Okay, so x plus x is 2x. Okay, so what you will observe here is 1 plus 2x plus x square by 2 factorial dx. Right? So now this is equals to 1. Certainly this is plus x square plus x cube by 3 factorial. Right? Okay, so now it is not in the same pattern. Okay, the previous pattern. Okay, now let's take the phi3. Phi3 of x is equals to 1 plus integration 0 to x f of x comma phi2. So x plus phi2. So x plus phi2 dx. So that is going to be 1 plus integration 0 to x. Now, if you go back and check, that's going to be 1 plus 2x plus x square by 2 plus, sorry, x square so plus x square plus x cube by 3 factorial, right, dx. Yeah, so this is equals to 1 plus, so this is going to be x plus x square plus x cube by 3 factorial, sorry, x cube by 3, right? Yeah, plus x to the power 4 by 4 factorial. Okay, right. Now, what you are obtaining now, I want to write now phi4 from here. So what I observe is first 3 terms are right now. So if you again go for this, so 1 plus, and you will have here x plus, right? 2x will come. So what will be 1 plus x square plus x cube by 3 plus x power 4 by 4 into 3 plus x power 5 by 5 factorial, and so on. So what will be the nth approximation I want to write now is Pn of x is equals to 1 plus x square plus x cube by, see, x cube by 3. So all these things are, you have this is x square by 2 factorial, x cube by 3 factorial. Okay, and this is x power 5 by 5 factorial, right? So we will track this, okay, up to this here, and this one we will see separately. Okay, right? So what will be Pn of x is going to be 1 plus x square plus you have x cube by 3 plus x cube by 3 plus x power 4 by 4 into 3 plus x power 5 by, you can say 5 into 4 into 3 plus, and so on, plus x to the power n by n into n minus 1 dot till 3. Okay, plus x to the power n plus 1 by n plus 1 factorial. Okay, so if you want to write phi5 of x, that also you can write now. Okay, right. So what is here happening is, now if you want to write, if you want to see, this is going to be convergent. So this is going to converge to where? So now first thing is, let me write it. I can write now this x square by, so if I multiply here denominator by 2 in each case, so they becomes 3 factorial, 4 factorial, 5 factorial, and so on, n factorial. Okay, and x square by 2. Okay, so what you will have is 1 plus x plus 2 times x square by 2 factorial plus x cube by 3 factorial plus and so on, plus x to the power n by n factorial plus x to the power n plus 1 by n plus 1 factorial. That's all. Okay, now we want to see the convergence. Okay, now what we can do is, I can add and subtract 1 plus x. Okay, so what will happen is, it is going to be minus 1 minus x plus 2 times 1 plus x square by 2 factorial plus and so on, x to the power n by n factorial plus x to the power n plus 1 by n plus 1 factorial. Okay, now you can see this is a constant term. Okay, means constant means it is independent of n. So where this does tends to, I just want to see now. So the first, these two terms will tends to the minus 1 plus x plus, now the second term here 2 times will tends to the 2 into e to the power x. What about this third term? This third term. So this term will tends to 0 as n tends to infinity. Why? Because it's a nth term or n plus 1th term of an infinite series, summation series. Okay, which we have seen that this is convergent. If this convergent, then the nth term tends to 0. So if you recall, summation an converges implies limit an is equals to 0 as n tends to infinity. And now you note that this summation x to the power n plus 1 by n plus 1 factorial will be is equals to nothing but the e to the power x. Right? It's a part of this. So n equals to, you can start with here, you can say from minus 1 to infinity. Okay, n is equals to minus 1 to infinity. Or if you don't want to be there, so you can write certainly n equals to 0 to infinity, and you have this x power n by n factorial, and this is the n plus 1th term. So if limit an tends to 0, limit an plus 1 also tends to 0. So we are using that fact. So this is the nth term or n plus 1th term of this infinite series which converges. So it's certain tends to 0. So the third term, this term, will not harm us. So this total, in totality, where do this converge is, this is equals to the analytical solution only, 2 into e to the power x minus 1. So as n goes to infinity, this will be dominated and this will be negligible, you can say. Okay, in the large cases, for large value of n. So this also tends to the analytical solution. So we have seen 2 examples now where this Picard's approximation actually tends to this analytical solution. Okay, so we can at present in this situation we can accept that this result is proven. Okay, we are not interested in proof here, so we have seen some examples here. Okay, right. Okay, so what next we can do is, here is we can derive now. so-called Euler's method now. Okay, so we can derive Euler's method. So I have this heading, Euler's method. Okay, so now for solving this, y dash equals to f of xy with y at x naught is equals to y naught. Okay, now you know this equivalent representation in integral form is equals to y naught plus integration x naught to x f of x comma y dx. Okay, right. So now let h is greater than 0, some positive increment we are taking. Okay, and x1 is equals to x naught plus h. Okay, the positive increment to x naught. Okay, and we are moving ahead. So x1 is the next point. So h may be very small, may be large. Okay, at present we are not working at the error analysis right now. Okay, so what will happen at large, what will happen at small, that you can see, at least analyze, you can analyze through the examples. Okay, right. So let h is positive increment and x1 is the next point to x naught. You can say with some means like with length is, you can say h with step h. Okay, so it's also called step size. Now, so then certainly you can certainly find out y at x1 is equals to y naught plus integration x naught to x1 f of x comma y t. Right. Now see, still this integrand containing unknown function, right? So you cannot integrate with respect to x at present, because if explicitly y is coming into the picture here. So if it is only a function of x, you can certainly do that. But it is, we are assuming that this may or may not be possible. So we are looking for the general case. Okay. Now, what is the assumption is, so assumption is here is this as follows. So let this interval x0 to x1, so we will extend it to x1 to x2 and x2 to x3 and so on. Okay, later. So let's say this on this interval, this f of xy varies so slow that it is can be approximated by f at x0 comma y by this point, or you can say the left hand point. Okay, so there are 2 points, x0 comma y0 and x1 comma y1. So f of xy is very so slow that it can approximate by the function at the x0 comma y0, which is nothing but the y dash at x0. Okay, if you recall, that's that slope strategy what we have seen in the graphical method. Okay, so that's assumption here on x0 to x1. So then what we will have, then this you can say some equation is star. What the star to be is then y at x1 is approximately now y0 plus integration x0 to x1 times f of x0 comma y0 dx. So if you look, see, this is a constant only now. It's a number, real number. So this is not involving any x or xy. So this can be certainly out from the integrand. And what is the integral is now y0 plus f of x, so x1 minus x0 time f of x0 comma y0. Now what is x1 minus x0 is this positive increment, that is h, f of x0 comma y0. So y at x1, so if we write in this way, y at x1 means we are talking about a analytical solution. And if we, so we have that y1, we will say that's the approximation. So y at x1 is the approximation take by y1. and which is going to be y naught plus h times f of x naught comma y. Okay, so now since we have not considered in this course the function of two variables, okay, otherwise it will be more simple to convince you that this is possible, that function f of xy is possible to be approximated by the value at the point x naught y naught in some cases, okay, by using the Taylor's theorem for function of two variables. I can make it comment here, okay, that's only, and from there only you can derive the error term as well. So we are not, I'm not going further for that. So what else you can do is, okay, yes, we can, I think we can certainly talk about the error here. So why? Because, so if you look at y at x1, what is that? Y at x1 is y at x naught plus h. Okay, now use the Taylor's theorem. Suppose that y is sufficient, you can say 2-time differentiable at least, or 2-time differentiable and second derivative is continuous. Okay, then you can certainly about the point x naught you can find the y at x naught plus h times y dash at x naught plus h square by 2 factorial by second derivative at some z. Okay, where g lies between x naught and x1, you can say, or x naught to x naught plus h, between x naught and x naught plus h. So by mean value theorem or Taylor's theorem. So this will be the error term. So we don't require here function of two variables. So certainly, and so this is what we are calling as y1 approximation. So y dash at x naught is nothing but f of x naught comma y naught if you compare with that. So this also can be obtained directly from the Taylor's approximation of y at x1 about the point x naught. Okay, right. So at least now you are agreed that okay, this is possible. Okay, so this is the first approximation. Now for the second approximation means you are going to continue now. Okay, so you take one more step ahead. So x0 to x1, then x1 to x. Okay, so you are moving in the interval, in the sub intervals now. You have divided AB, the complete interval, into n equal length sub intervals. Okay, and each interval, and you are moving step by step. You can also move directly from A to B as well. Okay, so that you can try how much error will be there if you directly jump to the A to B, and what will be happening in whenever you are starting with the nearest value. Okay. Now, one more thing is there, that Taylor's theorem. So this is happening because of Taylor's theorem. So Taylor's theorem gives you approximation about the point x naught, means in the neighborhood of x naught only. Okay. So if you go very far, okay, if h is large, okay, certainly this error is large. So you can analysis from here itself. If h you taken large, this error part, so this is called as error term. Okay, for the Euler method, this is the error term. Okay, now if you go with the h large, this will certainly be high because h square is there. Okay, if it is 10, h is 10, so 10 square is 100. Okay, so this is why it is required to move, okay, with small step sizes. Okay, so that suppose h is 0.1, so 0.1 square is 0.01. Okay, so in this fashion you can understand that to reduce the error you should move with the small step sizes. Okay, right. So now we have moved from x0 to x1. So in a similar fashion, similarly, so let x2 is equals to x1 plus h now. Okay, then what is y at x2? Again, if I apply the Taylor's approximation, so that's going to be y at x1 plus h. That's going to be y at x1 plus h time y dash at x1, okay, plus h square by 2 factorial y second derivative at z, so you can say z2, okay. So previous you can denote it by 1. So what is happening now? If you go with the from x1 to x2, so new error will also come now. So in total there will be large error if you take h step size to reach to the b. So you have to be small enough with the step size h. So this is nothing but so I can say this is going to be equals to y1 plus, since see we are only knowing the analytical value of y at x0, that is equal to y0, okay, but now we are also replacing y at x1 by y1, okay. So what we are saying is we are only interested in truncation error. So we have truncated, right? We are only interested in truncation error. We are not interested in rounding off error, other errors. So the other errors are ignored at present. Okay, means so earlier y at x0 is same as y0, but now y at x1, that's an unknown thing. So definitely you are going to use this approximated value. So there will be other error will take also place, because you are not using the exact value of y at x1, okay. So those things we can at present that we can ignore. So only we can worry about the truncation error. This is means like truncated here, so this is called truncation error, okay. So if you want to go for more higher accuracy, you can increase this, means instead of truncate here, you can truncate with h cube by 3 factorial y third derivative, okay, and so on. Okay, right. So that is a separate case. Then you will design some Runge-Kutta method and all. Okay. So right now we are only focused on this Euler's method. That's okay, fine. So plus h time f of x1 comma y1. So in general, so as I mentioned, y at x2 we are going to take as y2 only approximated value, because we don't have any other. Okay. So in general, so what are the steps? So given problems, you can identify what is f of x comma y, what is x0, x1, x2, x3, and what is the step size. Those things you can verify. So Euler's method give you yn plus 1 is equals to yn plus h time f of xn comma yn, with n equals to starting from 0, 1, 2, 3, and so on. Okay, and what is the step h is what is yn is y at xn, and what is xn is, you can certainly show that x0 plus n time h. So from x0 you have taken n step ahead, you can see. Okay, so we have taken here equidistant point only. Okay, right. Now see, we can, so this is called Euler's method. Okay, this is called Euler's method for a particular problem. So let me give you improvised Euler method as well. Okay, and then we will take some comparison between Euler's method and Euler's improved method, modified method. Okay, so it has some names, Heinz method as well. It also known as Trapezoidal Rule as well. Okay, right. So let me give you modified Euler's method. So it will be easily obtained by trapezoidal rule. So we have the equivalent equation is y at x1 is equals to y0 plus integration x0 to x1 f of x comma y dx. So over this interval, so instead of only using the left hand point, you can you can also use the right hand point and take the average. So what it is constructing is constructing a trapezium. Okay, so this means f of xy is replaced by you have this is x1 minus x0 is the height. Okay, and you have this is f of x0 comma y0 plus f of x1 comma y1 divided by 2. So if you recall trapezoidal rule, so you have replaced this integral by using trapezoidal rule. Okay, so that's going to be now equidistant point. So let's say y0 plus h by 2 times f of x0 comma y0 plus f of x1 comma y. That is equals to y. Now the question arises now. See, right hand side also involves the unknown things. Now what you do? So this is not a explicit scheme, you can say. Okay, previous one was explicit. The right hand side does not involve any unknown thing. So you can just feed. Okay, just start using with n equals to 0, you can find out the right hand side. N equals to 1, you don't need any other support, you can say. Okay, but here you require a support. You can't work with this. Okay, with the starting value it will not be the it is not possible because the right hand side involves the unknown. Now what you can do is, so instead of using y1 you can replace it by approximation. So approximated value now y1, you will take an approximation of y1, feed it here, that will give you new y1. So what you can say is you can predict the value y1. So on the right side, whatever is here y, so this we want to fix. So this you first predict the value by some other method, and then you substitute here. So that will correct it. So this is also known as predictor corrector method as well. Okay, so predictor corrector method as well. That also known. This is also known as predictor corrector method, and this is an implicit scheme. Okay, so you y1 first you predict and then you correct it by this. Okay, so now there are various ways to do that. So there are various methods available, single step you can say. So this is a multi-step method also. It's also known as multi-step method. So previous method is a single step method. So for getting y1 you have to take one step. For getting y2 from y1 you have to take one more step, and so single step method. So but here it is a multi-step. So it's also known as multi-step method. Okay, right. So now how do you predict it? So the famous why it is called modified Euler method, because it is going to be predicted by that explicit Euler's method. So what you can do here is you can, so I can just make it here now. Let me. So I want to predict this value now. So x1 comma y1. So I'm going to predict it, means like let me take it, let me say this is k minus 1, and let me take this y1k. Okay, so what is y1 0? I need y1 0. So it is for k equals to 1, 2, 3, 4 and so on. Okay, so y1 0 is given by y0 plus h times f of x0 comma y0. So if you accompany with the single step Euler's method, so that will give you this predict. This will predict. So predicting y1, and this is correcting y1. Means it is improvising the value y1, correcting y1. So this is why this is called a predictor and corrector method. Okay, now once you get y1 at 0, y1 means 0th approximation, you can say, you can, so for k equals to 1, so y1 1 you will get by feeding here y1 0. Okay, then y1 2 will get y1 1 here when you take k equals to 2. So k for, then you will use this value here, y1 of 1 you will use here value, and so on. Okay, so in general, what you can do is, I can just write a general method now. So in general, what is yn plus 1 at say k plus 1 is equals to y naught plus h by 2, not y naught. This is going to be yn plus h by 2 f of xn comma yn plus f of xn comma xn plus 1 comma yn plus 1 of k, where k is equals to 0, 1, 2, 3 and so on, with yn plus 1, 0 is equals to yn plus h times f of xn. Okay, this is for n equals to 0, 1, 2 and so on. So by putting n equals to 0, you will get y1 of 0. By putting n equals to 1, you will get y2 of 0 and so on. And then you are predicting the value, 0th approximation, and then you are correcting it. Okay? Right. So let's take the example now. Okay? Let's take one example now. Okay, so let's take example that's, let's say y dash equals to x plus y with y at 0 is equals to 1. Simple example. So if you compare what is f of x comma y is x plus y, x naught is 0, y naught is 1. Okay, so I want to approximate the value at 1. So as I told, so there are two ways. Either you take the step size means 1 itself, or you move in a slow manner, means like with step size 0.2 or 0.1 or even 0.01. So but now these, if you keep on reducing the this step size, you can't work on pen and paper. So definitely you require the support of computer. Okay, some computing software is required. Okay, so for when you are solving on pen and paper, so you can take 0.2 steps. So to I want to find y at 1. Okay, with h equals to 0.2, h equals to 0.4, and h equals to 0.5. Okay, and h equals to 1. So there are 3 step size we can take. Okay, so for the case h equals to 1, it is simple. So let me find out that first. So with h equals to 1, that case. Now, what is y1? So for h equals to 1, so then x naught is 0, and then x1 is x naught plus h, that is equals to 1. So I require to approximate y at x1. So that can be by Euler's method, that's going to be y naught plus h times f of x naught comma y naught. So what is that value is? Y naught is 1 plus 1 time f of x naught comma y naught is x naught plus y naught. So x naught plus y naught. So what is x naught is 0 and y naught is 1. So that is going to be 2. Okay, now you know what is the solution, analytical solution. Y is equals to 2 times e to the power x minus 1. Okay, so now let's see what is the analytical value here is. I'm just going to use this calculator now. So 2 times e to the power 1. Okay, so 2 times e. 2 times e minus x equals to 1, right? So 2 into e to the power 1 minus 2. So That is, so y at 1 is equals to going to be so 3.4365 something, so 44. So this is an analytical solution. So you can certainly look at what is the error here is 2, and this is 3. This approximated value by Euler's method is 2 here, and analytical value is 3.44. So that difference is 1.44 in absolute manner. Okay, right. So now if you take the step size h equals to 0.5, so let's take h equals to 0.5. So then you have x0 equals to 0, x1 equals to x0 plus h, so that is going to be 0.5, and x2 equals to x1 plus h, or you can say x0 plus 2 times h, that is going to be 1. So what you require to find y at 1 approximately. So means you require y at x2. So for finding y at x2, you require y at x1. For finding y at x1, you require y at x0, and so on. Okay, so we are going to use the Euler's method right now. So let's say this is going to be, so y1 so is equals to y0 plus h time f of x0 comma y0. So that is equals to, so y0 is 1, h is 0.5 into f of x0 comma y0 is x0 plus y0, that is 1. So that is 1.5. And what is y2 is y1 plus h time f of x1 comma y1 by using Euler's method. So that's going to be, y1 is 1.5. What is h is 0.5 time x1 plus y1. So what is x1 is 0.5 and plus 1.5 is 2. Right? So that's going to be this 2.5. So now it is improvised to previous one. So you have taken only half of the previous step size so far. Okay, right. So it is 2.5. It is which is more closer than the previous one. Okay, right. Now when you take the case h is equals to 0.2, for the case h is equals to 0.2, so you have x0 equals to 0, x1 equals to 0.2, x2 is equals to one more step with 0.2, so 0.4, x3 is 0.6, x4 is 0.8, and x5 is 1. So you want to find out what is y at x5. So for that, y at x4, y at x3, then y at x2, then all this stuff you have to find out. So what is y1 is equals to y0 plus h time f of x0 comma y0. So I'm just writing the formula once. So yn plus 1 is equals to yn plus h time f of xn comma yn. Okay, and I'm feeding the, okay, with n equals to 0. So y1 is equals to y0. So what is y0 is 1 plus 0.2 times f of x0 comma y0. So x0 is 0, so that's 1. So that's going to be 1.2. So what is y2 is equals to y1. So y1 is 1.2 plus 0.2 into f of x1 comma y1 means x1 plus y1. So 0.2 plus 1.2 is going to be 1.4. So that's going to be 1.2 plus 0.28. Right? Okay, so that's going to be 1.48. Now y3, so that's going to be y2 plus, so 1.48 plus 0.2 time. So x2 plus y2. So what is x2 is 0.4 and 1.48. It is going to be, that's going to be 1.88 into 0.2 plus 1.48. So that's going to be 1.856. Now y4, that's going to be 1.856 plus 0.2 time. So 1.856 plus y3, so plus 0.6. So that's going to be 2.456. That's going to be 0.2 plus 1.856. So that's going to be 2.3472. And what is y5 is equals to 2.3472 plus 0.2 time. So 2.3472 plus x4, y4 plus x4, that's 0.8. So that's going to be 3.1472. Okay, plus 0.8 into 0.2 plus 2.3472. So that's going to be something like 2.97664. 97664. So this is more closer than the previous one. So if you go with 0.1, it is increasing more. So error will reduce. Okay, at each step. Okay, right. So you have seen for now the case for Euler's method. So let's deal the case that's h equals to 0.5 or okay. So for the case h equals to 0.5, let's take the improvised method. Okay, so what was that is x0 is 0, x1 is 0.5 and x2 is equals to, or let me take h equals to 1. Okay, let me take h is equals to 1, x0 equals to 0, and you have this is x1 equals to 1. Okay, and now 0th approximation is I'm interested in finding y at 1, so I'm using that part only. So y1 at 0 is y1 plus h times f of x0 comma y0. So y0 plus h of f of x0 comma y0. So that's going to be 1 plus 1 into 1. So that's going to be 2. Now I want to correct it by using this. So now y1 of 1 is equals to y0 plus h by 2 times f of x0 comma y0 plus f of x1 comma y1 of 0. So that's equals to 1 plus 1 by 2 is 0.5 into f of x0 comma y0 is 1 plus x1 plus y1 0. So x1 is 1 and y1 of 0 is 2. So 1 plus 2 is 3. So 3 plus 1 is 4. 4 into 5, 0.5 is 2. So 1 plus 2 is 3. See, it is within one step, one correction, it is giving you 3. Okay, it is far more better than the previous, right? H equals to 0.2. Even for h equals to 0.2, you are not able to touch. So you are only able to nearby the 3 only so far. Okay, now what is y12? That's going to be y0 plus h by 2 f of x0 comma y0 plus f of x1 comma y1 of 1. Now you are going to use the previous correction, this prediction now. So that's going to be 1 plus 0.5 into 1 plus 3. So f of x1 comma y1, sorry. So x1 is 1 and 1 plus y1 1 is 4. So 4 plus 1 is 5. So 5 into 0.5. That's going to be 2.5, right? So that's going to be 3.5. So you're very much closer to the analytical solution. Now the error is very small. Okay, right. So see, here you require only few steps in correction. Okay, one step is prediction, and then you will see, you will realize with the other examples as well. So only 1 or 2 steps are, many times it is can be find out the very nearby values within few corrections only, means like 2 steps only or 3 steps at the most are required. Okay, so it is far good than the Euler's method, previous one. So similarly, you can go with the h equals to 0.5. Okay, and you can try that problem now. Okay, right. So this is here is defined as Euler's modified method, okay, which is also known as sometimes trapezoidal rule. This is also known as predictor corrector method. This is also known as multi-step method, so improved or modified Euler method. And Euler's method is a single step method. Okay, right. Fine. So let's now come to the first order differential equations and see how we will be able to solve them analytically now. So some certain special cases we are going to look at now. Okay. So, right. So these problems I can certainly state here. So the first part, y equals to c time e to the power kx for y dash x. So what is stating is verify that the following functions are solutions of the corresponding differential equations. So as I told already, okay, how to verify that y equals to this satisfy this means you have to substitute, find out y dash and see whether it satisfies the equation or not. So it's very simple. So I can just write down what is y is c time e to the power kx. Now if you differentiate is, that's going to be k times c e to the power kx, that's nothing but k times y. So it satisfies the equation. Similarly for this case also you substitute directly. Okay, that will give you the answer for this problem. For the second case, for the following differential equations, find the integral curve that passes through the given point. So you have been given with an equation, let's say first part. So you can use variable separable method. So dy by dx is equals to e to the power 3x. I can write into e to the power minus 2y. Okay, and I can arrange e to the power 2y dy is equals to e to the power 3x dx and integrate both sides. So that will give you lead to some constant c. Okay, so that will give you the integration now. So if I'm just writing the integration is e power 2y with respect to y is e power 2y divided by 2. This is e power 3x by 3. So what you observe is e to the power 2y by 2 is equals to e to the power 3x by 3 plus c. So when x equals to 0, y is equals to 0. So you can certainly find out c equals to 1 by 2 minus 1 by 3. Okay, so c value. So if you fit this point, you have to fit this point. What it says is x naught equals to, or you can say y at 0 is 0. So if you substitute this value here, so this implies that e to the power 0. So y equals to 0, x equals to 0. So that will give you 1 by 2 plus 1 by 3 is equals to 1 by 3 plus c, passing through this 0, 0 point. So this will imply c is equals to 1 by 2 minus 1 by 3. So that's going to be 1 by 6. So similarly for the next case also. So you can certainly e power minus y you can arrange with dy, 1 plus x square you can arrange with dx, and you can integrate both sides. And at the end, the constant can be determined by fitting this initial condition. So y at 0 is 0 here. So it may be different 0, 1, it may be different others. Okay, other points can also be the part. Okay, right. Now the third problem, determine whether the following initial value problems has a unique solution or not. Okay, so what I'm interested here for you is you have to look at these problems, okay, and try to see whether this satisfies the Picard's theorem or not. Okay, means the conditions you have to see. So for the first problem, let me take the first problem. So you can compare. So certainly f of x comma y is y by square root of x. Now see, you can certainly tell about the continuity of this by looking at the rational functions. It's like, okay, so see, numerator is continuous, denominator is continuous, so rational function is continuous everywhere except at the points where denominator vanishes. So only the point x equals to 0, it will not be continuous. So certainly when you try to apply the Picard's theorem, so that should not involve x equals to 0 at least, you can say. Okay, means that should not involve any point on the y-axis. Okay, because f of xy is not continuous. When you want to try to answer through Picard's theorem. Okay, right. So, and other thing is the point is given is 1, 2. So you have to cover the rectangle by this point 1, 2 for the Picard's theorem. Okay, so other thing is you then function is continuous, then you can try with the ellipsis condition f of x comma y1 minus f of x comma y2. That's going to be, you have this is y1 minus y2 divided by square root of x. If you take mod, this is there. So now see, when you're talking about this here, you can say, so this certainly will be less than equals to k time mod y1 minus y2 whenever you take x in such a way that 1 by root x is bounded by some quantity. So if x is not near to be taken as 0, so you can certainly bound it by some number. Okay, so you can try to get that interval, okay, where this 1 by root x is less than equals to k. Okay, so that's going to be 1 by root x. You can verify, right? 1 by root x less than equals to k if and only if root x is greater than equals to 1 by k, and or you can say 1 by k square is less than equals to x. Okay, and so on. You can work out roughly in inverse manner as well. So then you can certainly able to identify what will be the possible rectangle here. Okay, right. So we have, see, the next condition, second problem, it involves the x equals to 0. So Picard's theorem cannot tell you anything here because f is not continuous at x equals to 0. So Picard's theorem is not applicable. So what you can do is, now then you can try to solve this problem, okay, by using variable separable method, okay, and see whether that solution does exist or does passing through this point or not, whether it is possible to solve this problem. Similarly, for the third problem, fourth problem, and all these are all other cases of variable separable. Fifth problem we have already done. This has more than one solution and does not satisfy the Picard's condition. Okay, right. Okay, so let's end this session by giving one application here, which is called as population growth, which can be modeled by differential equations. So suppose that X0 bacteria are placed in a nutrient solution at time t equals to 0. So from the first statement, it is very clear. So at time t equals to, if x is a function of time, so x at t naught or t naught is x at 0 is x0. Initially, X0 bacteria are there. And that x equals to x of t is the population of the colony at a later time t. So x of t denotes the total population at a later time t. Means after initial stage 0 second, 4 second, 5 second, and so on. Okay. So there are further assumptions that if food and living space are unlimited, okay, means there is no means drought is there, so there is no, and means like starving is there. Okay, so if food and living space are unlimited, so there's no much fight. Okay, so and if as a consequence the population at any moment is increasing at a rate, so the population at any moment is increasing at a rate, so rate of increase you can say by dx by dt to the proportional to the population at that moment. So it is proportional to the population at that moment, that is x. So means there is some constant k such that dx by dt is equals to k times x. Find x as a function of t. So for this, it is very easy to find out the solution, that is what is nothing but x of t is equals to c times e to the power kx. Kt. E times kt. So now c can be identified by this initial condition. So x at 0 is equals to x0 implies c is equals to x0. So the solution is x is equals to x0 into e to the power k. So this constant we don't know so far. Okay, it may be is increasing at a rate k. Okay, so it may be positive, it may be negative, maybe okay, some number. So it may be decaying either, or it may be okay, or exponential increase there, or it may be exponential decay there. Depends. But so far, food and living space are unlimited here, and it is increasing. So k is greater than 0. You can say. Okay, so here k is greater than 0. Also, k is greater than 0. Fine, right? So we can end here session now. Okay, and then we will start looking for the now solution of some special cases of first order differential equations dy by dx equals to f of xy with initial condition y at x not equals to y. Okay, yeah, thank you. So